So, good morning to dear participants. And first of all, I would like to thanks to Geospatial sir and organizing committee of this specific webinar. And today's topic of my discussion is energy balance modeling approach for agriculture water management. So, very first, these are the contents which I would like to share in this my lecture, starting from the fundamental of crop water transpiration, the definition, and the traditional approach. What are the specific things? And if I'm talking about traditional approach, crop coefficient approach is the very premier and specific one, which is used from since earlier to estimation of crop yield transpirations. After that, the main theme and the title of this lecture, the energy balance modeling approach overview and its background part. After that, I will discuss about the remote sensing energy balance model. There are basically two type of models are there, one source model and two source model. So I just go through a few case study regarding a one source model, also the particular S-SEBI model, simplified surface energy balance index model, or metric model. Metric is the mapping evapotranspiration for using high resolution with internalized calibration. And after two source energy balance model, its overview, what kind of specific parameters are used and what are the basics practices regarding two source energy balance model, and how the formula and the details regarding seasonal crop water use. When we want to compute the crop water requirement or crop water use seasonal basis, how do you reach up to the seasonal basis computations? So that I will discuss, and after that I will discuss about the ET products, evapotranspiration products regarding regional as well as the global scales. That all products are freely available. You can easily download it and you can further use for assessment and comparison with your output of various ground-based observation as well as the remote sensing derived products. Okay, follow with a case study. I would like to also share after that the particular lecture. So very first about what is crop evapotranspiration. The crop evapotranspiration is simply the combination of two separate processes. One is your evaporation and second is the transpiration. If I'm talking specific evaporation, evaporation is the water loss from the soil surface, whereas transpiration is the water loss from the plant or crop surface. So combinedly it's called as a crop evapotranspirations. And the figure as it shows in the particular slides, it beautifully depicts the variation of evaporation as well as transpiration separately with the crop growth or crop phenology. If I'm talking the crop phenology, simply define the lifespan of the crop from sowing to harvesting. So as the crop growth takes place, how the particular evaporation and transpiration is varied, that is clearly depicts in particular figure. So at the time of the sowing stage, the soil is completely exposed with solar radiation as the energy lying on the earth surface or soil, the water which is available on the soil simply evaporate. So at the time of the sowing practices, because it's a zero vegetation stage, so at the time maximum evapotranspiration is the evaporation only. At the same as the crop growth takes place, LAIs increase. The dot line in the figure define the LAI variability and LAI variation with the crop growth. So as the crop growth takes place, the transpiration also increase and with the maximum vegetative crop growth stage. And after that, the maturity and sensing stage, there is slightly decrease in the transpiration and slightly increase with evaporation. And why it's completely a just opposite phenomena or process with each other in terms of evaporation transpiration, because as the crop growth takes place, the exposed fraction of the soil will decrease as the crop growth or crop area increase. So it's clear to define this particular figure how the evaporation and transpiration is move, or you can say the exit with the crop growth. So now the next is the traditional approach. The traditional approach specifically called it's a crop coefficient approach for the specific estimation of crop yield transpiration. So if I'm talking about the crop yield transpiration, it is simply a result of multiplication of crop coefficient with reference evapotranspiration. Now these are two specific terms. One is the crop coefficient, another is the reference evapotranspiration. So if I'm talking about the crop coefficient is simply ratio of actual evapotranspiration with potential evapotranspiration. And the Kc value, it's simply defined in FAO Irrigation and Drainage number 56 manual, it is clearly and fantastically define all their variability if I'm talking about the crop coefficient. And there is one more theory regarding crop coefficient is single or dual crop coefficients, as it is mentioned in the slide, the second formula, which is defined that ETC adjusted. If I'm talking about ETC adjusted, it is the multiplication of Kc multiplied with Ks multiplied with Et naught. So your Kc and Ks define the crop coefficient and with respect to soil as well as the crop, and Et naught is the same your reference evapotranspiration. As the figure is defined very clearly, if simply use the meteorological parameters, the radiation, temperature, wind speed and humidity at the time of a crop which has a specific characteristics, as we call it a reference crop with well water conditions, then we define it's a condition of reference of transpiration and amount of water loss, it's equals to the reference evapotranspiration. And then if you further multiply with the Kc value or Ks value, then we define specifically the crop evapotranspiration, normal or adjusted. One more thing I would like to share with this, the Kc value, it is vary with the crop to crop and also with crop phenological stages, starting from the initial stage to maximum vegetative stage to maturity stage. So as it's vary with the crop type, these values already defined in the literature. You can easily download and you can directly use the derived data sets or the value with terms of particular crop as well as the crop phenological stages. Now come to the second point. As once we call it the crop coefficient, second is the reference evapotranspiration. Then what is the reference evapotranspiration? FAO already defined very clearly regarding reference evapotranspiration that a hypothetical reference crop which with a assumed height of around 12 centimeter or 0.12 meter or a fixed surface resistance with value of 70 Simon per meter and albedo with a 0.23. So if the specific condition is met by the particular crop, we call it a reference crop, and at the time of the crop loss amount is reference crop evapotranspirations. Also, if we want to calculate the same reference evapotranspirations, we can use meteorological parameters judiciously and ultimately calculate the reference evapotranspirations at the formula defined in this particular slide, and the formula is simply known as FAO Penman-Monteith equations, and it is very accurate, or you can say most accurate. It is a physical based equations which has a incorporation of physiological as well as the aerodynamic parameters. The formula define the what kind of parameters we use. The parameters are enlisted in this particular table. If I'm talking about these all are the major data sets at the particular location specific. So if I'm talking about very first the location, altitude and latitude. So particular location specific, what are the atmospheric pressure values there? What are the extraterrestrial radiation or daylight hour, the capital N value. These three parameters we can calculate using the major data sets, and their formula and all the details are available in FAO Irrigation and Drainage number 56 manual, which is very comprehensively define each and every parameter in detailed manner. The second major parameter is the temperature, minimum and maximum temperature, which we simply measured using the dry bulb and wet bulb thermometer in Stevenson screen. And using that particular maximum and minimum temperature, we can further calculate the saturated vapor pressure, the saturated vapor pressure deficit, as well as the soil heat flux. These three parameters can further define further calculated using temperature data sets along the extraterrestrial radiation value. The third major data set is the humidity, the maximum and minimum relative humidity, and using that we can further calculate the actual vapor pressure at the particular observed area or observed location. Fourth parameter is the radiation or sunshine recorder. Using sunshine recorder, like we can use Campbell scientific sunshine recorder. Using that, we can further calculate the net radiations. So these parameters using the measure parameters, we can further calculate the calculated parameters as is defined in the table, and we ultimately calculate the ET naught using these all calculated or derived parameter using our measured meteorological parameters, and we can define what are the amount of reference evapotranspiration at instantaneous as well as the daily basis data sets. Okay, so now come to the, because I want to first briefly define what are the process of crop transpiration basics. Now I will once come to the our main title of, or the theme of this particular lecture, the energy balance modeling approach. So next I would like to discuss regarding measurement and computation. There is a clear-cut difference between measurement and computation. If I am talking about measurement it means using some specific instrument, a scientific instrument or a scientific methodology, we can exact measure the rate or amount of particular parameters. So that is the measurement. Where is the computation? We can derive the particular parameters using some initial measured parameters. So very first, if I'm talking about the measurement of evapotranspiration, there are numbers of methods are there, like lysimeter, a very specific instrument, and most precise and accurate method or instrument which is used for measurement of crop evapotranspiration at field scale. Then atmometer, pan evaporimeter, aerodynamic method, soil water balance method, large dimensional scintillometer, eddy flux towers. These are the specific instrument or methods which are used for measurement of evapotranspiration. Out of this, if I'm talking the large dimensional scintillometer and eddy flux tower, these are the most scientific and peculiar instrument which is used for measurement of evapotranspiration at particular foot scale or path length level. While if I'm talking about the computation, if I want to calculate for a bigger area, regional scale, then I have to go for the computation, because if I'm talking the measurement point of view, so we can measure a very, or we can cover only a few locations if I want to calculate for a state level or a regional level. While if I'm talking about computation, we can compute based on our few observations at the ground level, along with this scientific or modeling approach. We can further go for computation of regional as well as, or you can say, state level for ET estimation. Then in this computation process, there are numbers of methods are there. The very first are simplified empirical regression. In this, we can use the difference or a clear-cut variation between observed air temperature and land surface temperature. Along with this, the daily basis or instantaneous net radiation value, and we can further calculate how much latent heat or crop evapotranspiration rate at the particular regional scale or local scale. Then combined approach, where we can integrate the aerodynamic as well as the aerodynamic resistance approach, as well as the particular point specific observations to define the evapotranspiration combinedly. The third is the residual method of surface energy balance, which I would like to discuss in the following slides. And there is in particular residual method of surface energy balance. There is a two type of models, as I will discuss, the one source and two source models. So very first, the fundamental of energy balance modeling approach. It is also known as remote sensing energy balance approach, RSEB method. So the left figure, as it shows in the slide, is define the ET based on the residual of the energy balance. If I'm talking about the total energy which is available on the Earth's surface, is totally come from the sun, and we call it as a balance of incoming and outgoing radiation is known as a net radiation. And the total net radiation, if I'm talking net radiation, is summation of sensible heat flux, latent heat flux, soil heat flux, and other energy fractions. What are these? That I will discuss here. So very first, if I'm talking about the H, Le, and G, along with these three, there are also few energy components are there. These are the metabolic activities using by the plant in terms of photosynthesis, as well as the horizontal advection of the heat within the plant canopy. But their fraction is the less than 1%. So if I'm talking about the surface energy balance, we can majorly use three component sensible heat flux H, latent heat flux LE, and soil or ground heat flux G. And these three combinedly has a amount of 99% of total net radiations. So if we know out of three parameters, then we can easily calculate the fourth one using the particular equations. That's why they call it a residual of energy balance. So if I know out of four parameters three, then fourth one I can easily calculate. Okay. Then come to the right side figure. The right side figure define you the diagonal pattern of each energy flux component. So here, like you can easily see with the total 24 hour of the day from night 12 AM to next 12 PM. So what are the energy flux dynamics are there, or if their variabilities are there with the particular time. So Rn is the maximum, no doubt, because Rn is the net radiation which is available on the ground, and the same net radiation is further bifurcated in these three components, the Le, H and G. If I specifically define one by one, so I will one by one, the lambda ET or the Le latent heat is defined as the latent heat flux, or H is the sensible heat flux. Both are the H and Le is combinedly called its turbulent heat flux, and they are varied with crop growth from sowing to harvesting. How it is, like as its figure shows only the particular time specific when maximum crop growth is there, at the time your Le component is higher than H. Whereas if I'm talking about the crop sowing stage or crop harvesting or completely soil is exposed with the solar radiation, at the time H component is higher than Le. So their variation is just about their variations are there with terms of crop growth. And the G is the soil heat flux or ground heat flux, which defined around 10 to 12% of net radiations. And what are these particular parameters? These are the definitions of each and every component. So very first, as I already discussed, net radiation is the balance between incoming and outgoing energy which is available at the atmosphere, and we further calculate in the modeling approach at the ground level. Soil heat flux define you the how much energy heated the soil at the daytime and vice versa at the time the cooling process there at the night, in the night, during the night period. While the sensible heat flux, it means the conductive heat flux from the Earth's surface to the atmosphere. Or in the layman language, we can define sensible heat flux at the time of the noon hours or afternoon hours. If you roam outside of your home, you can easily feel the heat by your skin. So that same energy you can get, that means the sensible heat, the sense you the particular heat by your skin. So that component we define as a sensible heat flux. While is the latent heat flux is the flux of heat from the Earth's surface to the atmosphere and is specifically used for evapotranspiration of water. As the simply crop plant absorb the heat for their photosynthesis activity and the particular heat to maintain their body temperature, they simply evapotranspire. So that evapotranspiration is the latent heat of particular crop. So if I want to calculate using the same energy balance modeling approach or remote sensing energy balance approach, the L is equals to Rn minus H minus G. So that's why it's called it's a residual energy balance approach. Now these are the ultimate use of remote sensing energy balance model and their further applications. The very first, the crop transpiration. If you know how much crop transpirations are there at the field level, then you can easily judge how much water is required by the particular crop, as well as you can manage all your irrigation practices. So come to the all the points. The second, like crop water requirement, how much crop water is required during the particular season with respect to particular crop, because each and every crop has the different crop evapotranspiration rate, and that is also vary with climate to one area to another area. Then using water budgeting also, how much water is available with you, how you judiciously use your water. So that's come to the point of irrigation scheduling. So how much water if you know how much water is available with your in terms of surface, of subsurface water or underground water. So that water you can judiciously use in terms of 2, 3 or 5 number of irrigation for particular crop as per the crop requirement in terms of critical water requirement stages. Then irrigation water requirement, if I want to know irrigation water requirement, I have to know the total precipitation, runoff, the leaching, or you can say other kind of losses. Then I can manage the total irrigation water requirement of the particular field specific as well as the area specific. And if I know the crop transmission field level, then I can easily calculate the seasonal crop water requirement for the particular crop specific or the area specific. So these are the ultimate use of remote sensing energy balance approach, and that's why we are now scientific domain or various researchers are working on that domain using remote sensing, because the geospatial technology has the advantage or the capability to cover in terms of spatially as well as the temporal scale basis. Now come to the model type. These are two specific category. One is the one source model and another two source model. Now what is the difference between the one source model and two source model? One source model simply use the crop observations and this combinedly define as well as they combinedly define the evapotranspiration as a single unit. So these are the example. I just enlist one few models. It is not so like these are the only models. Numbers of models are available freely, where you can easily use the particular models and the equation methodology part, and you can compute the how much crop evapotranspirations rate are there for particular area specific, like S-SEBI model, CIS model, TBT model, C1 model, metric model. And metric, C1 and metric, these are the most advanced one. Metric because we can say the advanced version of C1 model. So in the one source model category. In the two source model category, there are numbers of model are there, and what are the specific definition of two source model? Two source model separately define the transpiration and evaporation process or their rate segregately, and also they use the information of crop as well as soil, or you can say the fraction of vegetation cover for computation of exact computation of evaporation and transpiration separately. And by combining the evaporation and transpiration, we can ultimately calculate or we can sum up in terms of evapotranspiration rate by the particular crop or by the particular area space. So the numbers of models are there like LXC, SIMRESET, two source energy balance, modified Twisted Taylor using the dual source energy balance approach, then this LXC. Numbers of models are also there along with this also. Now I would like to share some as in terms of case study of these one source model or two source model to define how we compute each and every parameters specifically. So very first, the S-SEBI model. S-SEBI model is a simplified surface energy balance index model, and this particular model has two major advantage over other type of remote sensing energy balance model. The very first is the geological data sets required for estimation of EOT fraction as well as crop transpiration if the surface extreme of vegetation cover and soil moisture are available. If you know the information of regarding vegetation cover, what kind of crop types are there, what kind of vegetation type are there in the respective area, then we can easily calculate with a methodology of S-SEBI model. And the second major advantage is to use the extreme temperature of wet and dry condition, not the particular pixel, but it's defined a wet edge or dry edge. How we define the wet edge, dry edge, that I will discuss in the next slide. So using that, we can calculate a static value of temperature for particular wet and dry conditions, or the value of image of particular each land classes at the define the particular model, the particular citation drawing at all in their paper, very first paper in S-SEBI model. And what are the particular dry edge wet edge that I will discuss in the next. This is the specific methodology for computation of EOT fraction using Landsat 8 imagery. So if I'm talking about a little bit remote sensing mode, or band 11 2 band in the particular category of 10 to 12 micrometer. Okay, so using Landsat 8 imagery, we can further calculate the specific parameters, and these parameters are defined in the particular flow chart of this methodology, like NDVI, albedo, emissivity, net radiation component. These all are component we can calculate. Along with this, the land surface temperature, and we can generate a scatter plot using the land surface temperature and the albedo.
Sir, your voice has been muted, sir.
Again?
Your voice has been muted. You are not able to hear
my voice, I think it is working. Yeah.
Me, it is working.
It is audible?
Yeah.
You are not audible, sir.
From my side, shares is okay. It is green signal is there.
Yeah, screen is also visible.
Am I continue? Am I go for? Am I continuing with this same slides?
Okay, sir. Now it's okay, sir.
Okay, okay. Okay. So, if I'm talking about the same methodology of S-SEBI model, so these particular specific parameters, or we can say it's a land surface parameters which is used for computation of 𝐶 fraction. So using that, we ultimately calculate the latent heat, and using the crop mass, the classified map of particular land use land cover in terms of particular crop type, we can further use and ultimately derive the crop transmission maps. How it is, you can see in the next slide one by one. So very first, these are the remote sensing derived and flux component. If I'm talking about very first, the net radiation. So there are four specific components: the incoming short wave, outgoing short wave, incoming long wave, and outgoing long wave. So as the formula is defined, the incoming short wave can be computed using the information regarding the solar constant, the viewing angle or the zenith angle, along with this the atmospheric transmissivity, while incoming outgoing long wave radiation can be calculated using the Stephen-Boltzmann equation, as we already know this law of physics formula, and using the temperature value of surface as well as the air. Then the next formula is soil heat flux. Soil heat, we can get the information of NDVI, albedo, land surface temperature, and the net radiation. These four components is used for ultimately computation of soil heat flux. Now come to the main component for is the 𝐶 fraction, and this component we can calculate with the value of albedo, as it is mentioned in here, the albedo value as well as the TS, the surface land surface temperature. So how we generate this kind of information using the land surface temperature and albedo, and when we generate this the scatter plot, and this is the scatter plot, is simply you can define a pixel based information of land surface temperature of the same pixel along with the albedo. If we make a simple scatter plot with surface reflectance, as it's mentioned, albedo or surface temperature, so all that points are visible here in between the particular bar lines. So using that information, how we define this particular line? There is two specific lines are there. One we call it a evaporative control, and second is the radiation control. So upper one is the radiation control, lower one is defined the evaporation control. Why do we call it a evaporation or radiation control? If I'm talking about the radiation control line, this is the upper limit or minimum of surface temperature with respect to the particular albedo value. Okay. Whereas your evaporation control, where is there no water stress conditions are there, while Just supposing the radiation control line, there is a water stress conditions are there. The particular pixel weighs informations. And how do we define the particular line? It's simply defined by make a binary or split up of our albedo range. Like our albedo range is vary from 0 to 1. So we make a fraction of with a 0.05 or 0.0, let's assume a 0.02. And if making the same fraction at the same particular bin size or particular bin, what is the LST maximum value and what is the LST minimum value? That simply defines LST maximum here and LST minimum here. Okay, so like particular at every bin you can define the LST minimum with this particular line and LST maximum with this particular line. And using that, we can draw a trend line. And that trend line define you the dry edge and wet edge. So this is the radiation control line define you the dry edge line. Where is your radiation, the evaporation control line define you the wet edge line. Okay, so what are the basics are regarding that? It is mentioned in this particular slide. If I'm talking about the wet pixel, at the wet pixel, your H value assumed to be 0. So your LE or lambda E, LE or lambda E maximum at the time Rn minus G. So there is no H component, H assume as a 0. While if I'm talking the dry pixel or the dry edge line, where is your LE is 0 and H max is Rn minus G only. So these are two contrast of LE max or H max. And this is the formula of delta, the EOT fraction, TH minus T naught divided by TH minus T lambda E. So TH minus T naught here TH defined is the temperature of H, or you can say the radiation control line. If I'm talking in terms of this figure, if like for example, if I want to calculate for this particular figure, so as the pixel or point is tends to towards the evaporation control line, the EO diffraction value is increased. Or if the EO diffraction value is increased, it means your ET or transpiration value is increased. Okay, so the same information as I defined in the earlier slide in terms of particular, if I know using the particular bin size the LST maximum and minimum value, and I make a trend line, a simple linear regression line. So this is a simple linear regression line as we already defined in Excel platform, MS Excel. The y is equal to mx plus c. The same equations are there. It is written in top of the particular slide. So using the particular TH and T lambda, the linear regression equation, we can ultimately calculate the EOT fraction. And this EOT fraction is further used for calculation of latent heat of flux and sensible heat of flux. Okay, but this information again now come to the particular, if I'm talking the remote sensing energy balance approach, this is a instantaneous approach because at the time of the particular fraction of second or instantaneous time, it give you the particular rate, the your transmission rate or sensible heat flux rate. Okay, and if you want to calculate for daily scale, how do you go for the daily scale? That is defined in the further. Like if you want to calculate for daily basis, then you can use number of various researchers already defined the net radiation for daily scale. So if you calculate the net radiation with daily scale, how much net radiations are there available on the particular location, then you can calculate the daily evapotranspiration for particular area specific or regional specific. And in this particular same methodology, because Remote sensing give you the result in terms of particular modeling approach as a computation basis, or it's a simply compute. So you have to validate your result using some specific ground-based observations. So here we use specific ground-based observations of large aperture scintillometer in this particular methodology. So large aperture scintillometer is a peculiar instrument which has a path length of around 990 meter. Here, as we installed in palm of IARI in a collaborative project with IIRS and IARI New Delhi. But if I'm talking about the path length of large aperture scintillometer, it's vary from 250 meter to 6,000 meter. Okay, but in palm of IARI we installed is a path length of 990 meter, and the particular instrument measure the sensible heat flux based on the principle of mononomial similarity theory, or you can say specifically measure the structure parameter of refractive index. So this is some basic, or you can say physics-based parameter or physics-based derivation. There are parameters are there which is observed by the particular instrument, and they convert or they ultimately calculate the sensible heat. And if we know the net radiation or G value with the observed at the ground level using net radiometer or sensible heat flux plate data, then we ultimately calculate the latent heat flux, or you can say crop-Hugo transpiration. So once we observe the data sets using this is your transmitter and this is the receiver end, the C is the receiver end, and if you after receiving the particular data sets at the 10 Hz frequency, or you can say at 10 Hz frequency, and we convert the data sets at 5-minute interval. Using that data sets, we can further process in evaluation software, and in evaluation software we can specifically generate the file for latent heat of flux or output transpiration measured value, and these are all a diagonal pattern of the particular data sets which we have already published, and this is the data sets of 2014-15 for respective, as it's mentioned the month 1 to 12, it is the starting from the Kharif season from June to next May. It's a completely Kharif and Rabi season combined, but it's very peculiarly or specifically defined the net radiation, soil heat flux, sensible heat flux, and latent heat flux. And in latent heat flux, you can easily define that as the crop loss takes place, the LEs increase. Again, at the time of maturity or harvesting senescence, it's decreased. Again, with the next crop of Rabi season, the LE value is increased, and with maturity, senescence, and harvest, the value is decreased. So this is a clear-cut sinusoidal pattern of latent heat flux with the complete crop season of Kharif and Rabi. And for that, using the same large scintillometer, this is the complete energy flux pattern of seasonally from June to next May. So complete Kharif and Rabi season, you can easily define the RH, G and LE variability within the particular area, especially the particular path length of 990 meter. And we can also compare the LE with LAI, the leaf area index, or you can say the complete leaf coverage. So it's as a positive correlation, significant positive correlation of function of intervention value of 0.8, while the sensible heat flux or LAI, the leaf area index or H, has a significant negative correlation with function of determination of -0.79. It means as the LA is increased, the H value is decreased. And if you define in this particular right upper figure, like the bone ratio, as the crop loss takes place, bone ratio decrease because H component is decreased, because your blue line define you the blue dotted line define you the H value, while is the bar define you the LE value. As the crop loss takes place, LE value is increased, and using the particular LE value, we can further define the ET in terms of mm per day rate, and it's defined for Kharif and Rabi season very specifically. Very significant result we find out for particular season, specific in Kharif and Rabi season both. For the same information of the 2014-15, we can further assimilate or use for validation of S-SEBI model, and we can define Once the IRI New Delhi is our validation site, and we calibrate our data sets for, we also make a simulate or validate our data sets in terms of our observed data sets at particular two different crop pattern. Our cropping pattern, one is the sugarcane wheat, the E defined with the sugarcane wheat, whereas we define the rice wheat cropping pattern. And very clear cut, this is define you the daily basis, daily ET rate for sugarcane wheat and rice wheat, and these all are the map, crop transmission map for particular day specific of complete season of Rabi and Kharif and Rabi season. And we go for the validation of the data sets using large flow centimeter. We find out a very good option, correlation coefficient with 0.85 and agreement index is 0.86 for our Rabi season data sets. Because when you go for the validation, always you have to use a clear sky satellite data sets and there further derive ET or derivative fraction data sets with your and compare with observed data sets. And then we find out also a new type of setup for measurement or in terms of validation, we make a 3x3 window plot. 3x3 window plot, it means I simply define you as Landsat 8 has a 16-day temporal resolution, or you can say every 16 days you will get a data set for the same point or same region, or the particular spatial resolution of the particular satellite data is 30 meter, or because they downscale as they measured or data sets in the 100 meter in thermal band, but they downscale data set and provide you data at the 30 meter resolution. So we make a 3x3 meter window. 3x3 meter means 90 meter or 90 meter of the same path set of last, and like this we can iteratively validate our product with satellite derived UFT fraction with 3x3 window, 5x5, 10x10, 15x15 and so on. And out of this all we find out 10x10 or you can say 300x300 window is find as highest correlation coefficient or agreement index along with this highest model efficiency for particular area specific in terms of validation of S-SEBI model product. So like this we validate our product, and this validated product and we extrapolate with or we can compute the result basis how much crop transmission data are there with terms of crop specific also, area specific also, or season specific also. So all kind of things can be done using the same kind of data sets in different kind of manner. Now the next most advanced one-shot type of model, or you can say advanced version of C1 model. C1 first originated by or derived by the Prasad in 1995 in their paper, which is already published in Journal of Hydrology in calibration on validation part. So the particular C1 model simply is a surface energy balance algorithm for land, and the metric model is the mapping your transportation at high resolution using internalized calibration. Metric model, or that metric model is derived by the Allen, researcher, the great scientist in the field of evapotranspiration or evapotranspiration, or you can say requirement. So they derive the particular metric model, and they specifically use a pixel-based information of in terms of dry pixel and wet pixel, and they derive the difference between surface temperature as well as the air temperature of particular point specific, particular pixel specific, and define the dry edge and wet edge. So how it is? They execute the particular model. I will discuss one by one. So very first assumption regarding the particular model, like there should be a few assumptions has to be made when you go for the using the geospatial technology, as well as when you go for the result basis estimation, correct estimation of your transpiration rate. So variation in the land surface temperature is linearly related with difference of your land surface temperature or air temperature. It means there should not be any abrupt changes in terms of their variation with particular point to point land surface and air temperature. Then sensible heat flux varies linearly between hot and cold reference pixel. Hot and cold reference pixel simply define hot pixel a crop area, crop land which has the minimum LE or maximum H value, whereas your cold reference pixel is just vice versa, or you can say maximum LE value or minimum H value, or you can say 0. LE value, H value is 0 for the cold reference pixel. The complete contrast 2 points, and that same 2 points has to be lies on your particular same satellite imagery. Then you can calculate a correctly estimate the crop Echo transpirations. Now, actual transpiration for hot reference pixel is 0, no doubt. And if you calculate the same actuality for the cold reference pixel, that should be as equal to the reference transpiration is 1.05, because sometimes the value exceed by more than 1. That is defined in the same FAO irrigation drainage paper 56, as well as in various peer-reviewed journal regarding crop transpiration estimation and validation. Then reference transpiration fraction ETRF is constant throughout the day, that you have to assume and you have to define with terms of data sets. And as well as the last and important point, the actuality for the study area varies in proportion to changes in the reference city at weather station. If the crop area, if you exceed the crop area, or if your crop area is increased more than 50 by 50 km, 100 by 100 km, so you have to use more number of weather station to generate the reference transpiration and extrapolate the data sets for complete areas. So these are the few assumptions that you have to be made when you use the metric model. Then the energy balance component, net radiation, as we already discussed. Here, one point I would like to add, in the net radiation calculation, they also added the digital surface model data sets, how much elevations are there with the undulated surface, that particular data sets, as well as the atmospheric pressure data sets for computation of net radiation and its component. So these two specific parameters are also additionally added for net radiation computation. Then second is the soil heat flux, like earlier as I defined, you use the albedo value, NDVI value, land surface temperature value combinedly, and we can further calculate G value or soil heat flux value. But here they use another much more especially derived or using the LAI value, the ground based observation of leaf area index with terms of particular crop specific, and they generate the soil heat flux map for particular area specific. Now to come to the next, the sensible heat flux. The H is the total of rho multiplied with Cp multiplied with dt divided by RAH. Your rho here define the air density, which is already mentioned in terms of in various review literature around value of 1.004 or 3 in kg per meter cube, and Cp is define you the specific heat at the given pressure is around 1004 joule per kg per degree Kelvin, and dt here specifically define the air temperature difference between two height particular point at near to the crop surface and above the particular crop surface. So at the time, at the same instantaneous time, how much air temperature difference are there, using that and define that dt. Whereas your RAH is the aerodynamic resistance of heat transfer and the value in terms of Simon per meter. So if I'm talking about this particular sensible heat flux formula, 2 parameters be known and 2 parameters are unknown for us. So how we calculate 2 unknown? If we know out of these, then we can easily calculate the sensible heat flux. So how we calculate these particular parameters that I define in the next slide. But again, what are the specific things? How we define the cold pixel and hot pixel and their selection procedure, which is very much critical and important to define, and on the basis of the same dry and wet pixel value, we can further extrapolate our complete regional basis data sets and the particular in terms of map form. So if I'm talking about the anchor pixel of cold, there's few 4 specific steps are there, the processes are there. So in this very first, we have to filter our area of interest, like total of area, like we can segregate a 10 by 10 kilometer square area or 50 by 50 kilometer, 30 by 30 kilometer square area as in terms of area of interest, and the same area has to be a same cold and hot pixel within the same confined boundary. When we use geospatial technology or satellite imagery, any kind of satellite imagery, which has a thermal data set like Landsats, legacy data sets are there, MODIS data sets are there, ESTER data sets are there, which has the thermal band data sets. So in this particular cold anchor pixel, we have to choose top 5% of NDVI pixel. Top 5 NDVI pixel, it means simply NDVI is the proxy of vegetation figure, or you can say as the NDVI value is increased, more the crop growth or crop figure is there, which we present in terms of NDVI value. So 5% NDVI pixel within our area of interest, we have to redefine, and we define and calculate the average temperature among the coldest 20% of based off TS. TS is the land surface temperature. So using that, the top 20%, the particular coldest, we have to choose, and within this we have to make a range of plus minus 0.2 degree Kelvin with a average land surface temperature and albedo within a range of plus minus 0.02. So there should not be any kind of abrupt changes in the land surface temperature as well as the albedo. So based on that, we have to choose one pixel with a homogeneity among its neighboring pixels. So like this, we can define the cold anchor pixel. If I'm talking about a hot anchor pixel, we have to choose lowest 10% NDVI, like less the NDVI value, which is around near to the. If I'm talking NDVI value, it's vary from -1 to +1. Less than 0 value, mostly defined about the water pixel. So more than 0, we want to define the soil, and as the NDVI increases, as defined the fraction of vegetation cover is increasing. So NDVI value is around like 0.1 or 0.15, 0.2. As the particular time of the satellite image we already downloaded or we used. The lower 10% data sets we have to use. 10% data set have to use in terms for filtered area of interest. And along with this, we have to choose the hottest 20% of land surface temperature pixel value. And again, the same a range of plus minus 0.2. There should not be any kind of abrupt changes in the land surface temperature. And based on high homogeneity of our neighboring pixel, we have to choose one single pixel, or you can say one particular point in satellite imagery. So like this, we have to choose cold or hot anchor pixel to define the RAH and the DT. So your RAH is aerodynamic resistance, which is based on the particular two height difference, aerodynamic variability in compression of the U star is the frictional velocity, and K is the one common constant, which are based like the values of 0.41. And these all are the values are available in the metric model or 𝐶𝐶BL model manual. And these all value how to derive the particular things. This information also are available there. So, but my point of concern here, how you define the DT, the range of DT or the particular DT value. So the upper side figure define you a trend line of variability in terms of DT on y-axis or land surface temperature on x-axis. So the DT is the TZ1 minus TZ2. It means a particular height of Z1 or Z2, whatever the temperature difference are there. Okay, and DT, the particular as you define the A or B, these are the coefficients when you generate the particular line, and using the particular line you can further derive your RAH and particular RAH value as well as the same as you earlier defined in this formula, the DT. So DT RAH you can calculate using that with a internalized calibration procedure and ultimate calculate the latent heat using the particular model. There is an advantage in terms of all other kind of the one source type of model over the metric model. So metric model has specific advances, which is mentioned there, like it's required a minimum ground-based observations. It solves all kind of energy balance model, all terms of energy balance model, like using that particular model, using internalized calibration, we can generate the H and LE component, and for the R and G. So all four components segregately we define using the particular model, metric model. And also, this model is very much efficient to work in undulated topography or undulated surface. So, as I already briefed in the earlier slide, like in undulated topography, it's counter the point of DSM, distal surface model data sets, as well as the atmospheric pressure, because atmospheric pressure also varies in terms of altitude. So, these variability also counter in the same model. A specific disadvantage of this kind of model are there. One is the uncertainty from the user selection of hot and cold reference pixel. This is the most difficult task. Once you counter the particular part, then you can easily calculate and accurately, most precisely calculate the crop transmission of all kind of energy balance component of particular model. And also the second disadvantage is the time intensive to apply at basin scale. Because when you have to go for a basin scale, a bigger area, then you have to go for the internalized calibration. So the internalized calibration require number of iteration. You can say hundreds of iteration can be required for finalization of your LE and H component in terms of the model requirement. So that is the specific advantage and disadvantage of metric model. Now come to the second category of remote sensing energy balance model, as known as two source energy balance model. As I already briefed you, two source energy balance model segregately define your evaporation from the soil and transpiration from the crop surface or canopy cover segregately. So how do they define using that? So in this particular model, you have to segregately define your vegetation cover or the soil fraction segregately. And because there are some limitations are there when you use the single source energy balance model at the time of the initial stage when the vegetation cover are minimum at the time, because the maximum contribution of the evapotranspiration is the evaporation from the soil side, the evaporation side. So sometimes the model simply extrapolate, the overpredict, simply overestimate the data sets as its normal value. So to counter the particular such kind of problem, along with this, at the time of the harvesting stage also, or finishing stage also, or fallow land area also, sometimes it's overestimate from its actual value. So to counter the particular such kind of problem, two source energy balance model has been designed, very first designed, and now it is number of models are available, because very first in 90s scientists are already developed various kind of model till now a numbers of model, as I already briefed in previous slide. So here they segregately define the evaporation and transpiration. It is mentioned in the right side of this slide, like LEC or LES. So how we define the crop and vegetation segregately? Here, if I'm talking about one specific model like modified Dichter-Taylor method using the trapezoidal methodology, trapezoid scatter plot, here they specifically define the crop or vegetation fraction separately and soil, and they same define the equations and in the S-SEBI model as I defined the dry edge and wet edge line, same they define for crop and vegetation segregately. Using that, they derive the particular evaporation and transpiration, and combinedly we got it as total crop transpiration rate for particular area specific. Now come to the seasonality or crop water use. If I want to calculate the crop water use, these are the formula as I mentioned in the slide. Because earlier as I defined the instantaneous evapotranspiration in this particular model of S-SEBI or metric or other model, when you calculate the reference ET fraction, how much this is a formula, ETRF is a ET instantaneous divided by ETR, and ETR is the reference for transpiration at the time of the particular image, and at the time of image acquired. Like if I'm talking about Landsat image, Landsat 8 is acquired at their acquisition in the, if I'm talking about Indian in Greenwich Mean Time or GMT plus 530, at the time in Indian context, simply observe the image at 1048, around 1048, and the same information also available in the metadata of the satellite data, Landsat 8 or Landsat 7, which you already download in from the USGS web portal. So this information is also defining you at which time the data sets are observed. At the same time, you have to define the reference ET fraction. And if you want to calculate the same ET for the 24-hour or even daily evapotranspiration, then you have to compute the ET24, the cumulative 24 evapotranspiration, and that cumulative 24-hour ETR you have to compute using the ground-based meteorological parameter with a high frequency, or you can say a 5-minute or 10-minute interval data sets at the particular location specific. So using that, you can cumulatively define how much 24-hour level ETR value. Along with this, the meteorological data sets using some specific like reference ETR, already developed plugins or softwares are there, which you can easily download and you can use. And also like top software are there. So using meteorological observations at particular location specific. You can use as an input in Crawford model or reference city model, or you can calculate the reference for transmission on hourly basis or daily basis, or even monthly basis also. So using that data sets, you can further define the daily basis crop transmission, and using the summation of the crop growth, you can define how much season basis crop transmission is there. So based on crop transmission data sets, you can define this is the crop water use of the particular crop in respective area. And if I'm talking the crop water requirement, so if I'm talking crop water requirement, you have to add the part of crop, respiration as again, or the water loss in terms of irrigation application data. So that is a total your in terms of crop water requirement by the particular crop. And especially crop water requirement, they use the precipitation data sets to define CWR crop water requirement. So this is a whole nutshell regarding the seasonal evapotranspiration data set calculation, starting from various one source model, two source model respectively, and ultimate calculation using the reference for transmission data sets for seasonal crop transmission or crop water use at crop specific areas in area. And one type of results I would like to share with you, like we already defined for Western UP area, which include the bottom left side defined that the Delhi area, and this is other area is the complete Western UP district, like area of area of Muzaffarnagar, Bagpat, Shamli, Meerut, Ghaziabad, Hapur also. So this is the variability, or you can say in terms of map form, generated using S-SEBI model or modified Taylor method for crop water use of seasonal basis. And this is the data sets as we derive for season of 2017-18 for particular Rabi season only. So this is a crop water use of Rabi season in respective area. So by pixel or particular area to area we can generate, and also we can compute for crop specific how much crop water use are there in respective area at particular field level also or district level also. Now these are all the these are the all in terms of research findings in when we use some specific remote sensing energy balance methodology as we discussed earlier. Now come to the some specific ET products, like the ET products which are readily available, or you can these are the free of cost, so you can easily download and you can compare your output, your findings with the particular data sets, and you can make a judgment that either I on the right path or on the wrong. Like my computer, as I already computed the data set, that is accurate, near to accurate, or completely wrong. So using the ET products also we can use the particular already set their data sets. Like the very first, this is the MOSDAQ website portal. As I show in the screenshot, the MOSDAQ is a ISRO web portal for specific, and that particular web portal you can download the daily basis or the monthly basis PET data sets, potentially for transmission data sets for Pan India easily at the particular website that is there. You just use your generate a registry yourself, go for the username password, and at the particular MOSDAQ.gov.in you can download the data sets of monthly and daily potentially for transmissions. So the next is the eFlux. This web link is also there in my slide. Here you can see or you can visualize the ET product, and this is the ET product of using metric model, specific as I already discussed in my slide. Metric or most accurate or advanced one of one source type of remote sensing energy balance model, and these are the set products are there, like these results like in terms of albedo, NDVI, land cover, surface temperature, then ETRF, ET actuality, all the image. Like here I show you, this is the actuality image of the Western UP. This is the part of Delhi, and this is the Western UP area, and this is like Eastern UP, Lucknow and all. So like this, all the data set, the particular tile specific data sets are available in here, and but you can, as the incursor shows, the blue incursor shows, this only data sets you can download at once. And if your area is like 10 by 10 or 5 by 5 kilometers area, you can define in terms of the ROI, and you can easily download the set product of actuality derived from metric model, and you can compare with your ground base of you can compare with your model based observation also. Then come to the next, one more type of portal, one more type of ET products. The portal is from the USAID for monthly actual transmission. This is also a monthly actual transmission products, and this is the bottom right bottom one. Here define the web link of the website. Here you can go and you can easily download global basis or global scale on particular monthly actual operation data sets. And if you want to calculate like how much monthly actual transmission data sets are there in particular my area and how much variability are there with the particular month to month, season to season, or year to year, all kind of data sets you can download and you can visualize also in terms of results. Now, one more type of results or the ET products. The what is evapotranspiration? It has a spatial resolution of 1 kilometer pixel size, and this is also a global product. You can download the data sets. I also give you the URL of the particular website. Here you can download as per your area of interest, region of interest, or you can say your study area. You can download the data sets and you can compare and you can analyze the data sets also how much variabilities are there. So number of kind of works are available in the using the set derived product also, like using ET data sets you can further think how much evaporation rate are varied with the season to season also, and what is the probable reason, or if a area which is normal in terms of crop growth, and sometimes it shows the lower evapotranspiration. It means might be there may be stress conditions are there. So in terms of the domain of crop stress, maybe due to abiotic stress, you can define these may be stress condition in a particular area. So such kind of work, a new kind of work you can think using the set derived product also. Now come to the practical demonstration as I already discussed by organizing committee. They already briefed me that I have to add some products in terms of data sets and how we execute like such kind of model or such kind of results. So very first, I would like to tell you the GIS interface. A numbers of GIS softwares are available nowadays in the market. Like some are free of cost or some are paid. But you can use any kind of software and their plugins. Along with this, the freely available satellite data sets and generate your results easily in the particular GIS interface. So very first, I would like to share a complete steps in how you proceed each one by one when you generate the crop evapotranspiration result ultimately. So very first I choose an image, I download an image of Landsat 8 sensor and the date of acquisition is 20th Feb 2018. I simply use the USGS portal and the image is freely available on their web portal. I download the image, I make it as a FCC. This is the same area of your Western Uttar Pradesh and the NCR, Delhi NCR area. So this is the image in terms of FCC. FCC is, we call it a false color composite. When you composite the 3 band in GIS software like near infrared band, red band and green band, in particular 3 color, NIR band into red band into green and green band into blue color, then the image look like so. So where there is a more reddish color is, you can see there is a more vegetation or crop growth is there in particular area specific or satellite image specific. Okay, so you can easily judge with this particular image by a visual interpretation. Next, using the particular NIR band or R band. NIR band is your near infrared band and R is your red band. Using the particular 2 band NIR and R, I simply generate the NDVI indices, and these indices very much important and very much critical to define ultimate your last output. NDVI is the normalized difference vegetation index, and the formula is NIR minus R divided by NIR plus R, and the band value of particular wavelength like near infrared band or red band in terms of surface reflectance data sets. And these data sets is also available or to use that particular portal freely. So as I show you the results is you can easily download at your end also, and you can derive the results very easily with a prior knowledge of their data sets. Then emissivity. Here I use the same my earlier NDVI data sets, and I use the methodology NDVI based emissivity. If you simply type on Google NDVI based emissivity, you can find out the particular formula or particular details regarding that, how we generate the emissivity.
Excuse me, sir.
Yeah.
We are getting echo of your voice.
My voice is again issue. I think now it is okay.
Yes, sir. Now it's okay, sir.
Actually, sometimes the bandwidth issue is there. The internet connection might be lost. Now it is okay. Hello. Now it's okay because
Yes, sir. It's okay.
Okay. So again, yeah. Using the NDVI image, I further use the NDVI based emissivity method, okay, and generate the land surface emissivity image as it shows in the slide, okay. And that formula, if I'm talking specifically the NDVI based emissivity method, I simply categorize my NDVI value in three classes: less than 0.15 value, NDVI value is less than 0.15, 0.15 to 0.5, and more than 0.5. So like I make it three category, and these three category specifically define the soil, mixture of soil and vegetation, and third is the vegetation. So like three classes I define, and the specific coefficient are used, which is already there in the various peer-reviewed journal or their publications. You can use directly, and you can generate the emissivity image. Using the land surface emissivity image with some transmissivity or incoming or outgoing, or you can say incoming or downwelling or upwelling irradiance value, or incoming or outgoing irradiance value, which is derived in from a particular web portal. Hello?
Yeah.
Again?
You're getting echo of your voice, sir.
Yeah, why it is so high?
Here it is clear. Hello, Vikas.
So using that emissivity,
It's okay, sir. But actually, we are getting
actually I am using the laptop only.
Pass teacher. Because we are getting one quantity pass. Local network here.
Sir, I request all participants to please go your mic on mute yourself. That sir can only speak, so that might be creating echo.
Okay. Should I continue?
Yes, sir. Go ahead.
So LST image, we use the NDVI and emissivity, land surface emissivity value, along with this the upwelling and downwelling radiation, which is derived from model, and the tier value is also readily available on the web portal and the particular website of Atom-Core GSFS. And all details are there in various research paper, in also my research paper also, or in various peer-reviewed journal research paper also. So no need to worry about regarding the data sets or their how we derive the data set. All set of methodologies are written form is available in various papers. So using that information, radiation information, radiance informations, emissivity and NDVI, we can generate the land surface temperature. Now come to the point, like what are the, if I talk the land surface temperature, simply define you the temperature of your surface, or you can say the skin temperature. So if I'm talking about land surface temperature, it is always higher from your air temperature at the daytime and vice versa in terms of night time. So night time your air temperature is higher, land surface temperature is lower, while in the daytime your air temperature temperature is lower and surface temperature is higher. Like as here we use Landsat 8 image and the time of acquisition is around 10:48, 10:48. So at the time your LST is always higher from air temperature. So like you can cross check your data sets, like as I already proceed or already analyze data set is okay or not. Like this you can iterative manner you can check your results also. Then come to the albedo. In albedo simply define you the fraction of radiation in with total radiations in short wave length, particular short wave length, not long wavelength. So albedo calculation here we use from band 2 to band 7 of Landsat 8 with some specific coefficient, and these coefficients are also available in various research papers. So, and this also you have to iterate according to your area specific and derive and define the results also as it is there in this particular image. So albedo value is vary from 0 to 1 as we derive using the Landsat 8 short band 2 to band 7. Band 2, 3, 4, 5, 6, 7, all 6 band. Now come to the net radiation. Your net radiation is the total of incoming and outgoing radiation, and as the particular formula is, as I already discussed with you in my earlier slide, that you have to compute incoming short wave, outgoing long wave, incoming long wave, and their details are available. Using that you can generate the image of net radiations of particular area specific or particular your satellite data. And come to the G, using the NDVI data sets along with NDVI you can generate the G or soil heat flux image for respective area. Then come to the EF value, EF image, the EF diffraction image. As I already discussed, this is the result of S-SEBI model, simplified surface energy balance index model. So I used that particular same scatter plot with as y-axis is land surface temperature or albedo on x-axis. So we make a scatter plot and we define the dry age and wet age. Okay, and using that particular information, so I derive the EF diffraction. And with EF diffraction, multiply with Rn and G, I ultimately got the result of instantaneous EF transpiration of my area. As the same GIS photo you can easily see in terms of color visualization also. Okay, so like this we can generate starting from download the data sets. We can proceed from download the data sets to NDVI, emissivity, your land surface temperature, albedo, net radiation, soil heat flux, EF diffraction, or maybe your latent heat directly, or ultimate the EF transpiration image. So like in the following steps you can conclude or you can proceed your research for generation the crop EF transpiration image. And this using crop EF transpiration image, this is instantaneous crop EF transpiration image result. So you can using the reference for transpiration, you can further calculate by a simple mathematical calculation in the same image using raster calculator or band math in GIS platform. You can generate the daily EF transpiration and you can sum up for a season and you can define this is my crop attributes for particular crop type. Okay, so like this you can proceed in a very precise manner from download the data sets to up to the result of crop EF transpiration. So this is all from my side. Thank you very much for your paying keen attention during my lecture. And this is my mail ID abhidhanodia@irs.gov.in and my landline number, office landline number. You can contact with me or through my mail ID or telephonic conversation, and I will happy to share each and any kind of information with you. Thank you very much.
Thank you very much, sir.
Thank you.
Am I audible, sir, now?
Yeah, you are audible. Is there any question, sir?
Am I audible, sir?
Yeah, you are audible.
I would like to thank you very much for such an informative session you have just conducted. You have said quite in a very manner, sir. You have reviewed the entire topic of web of classification, sir. Then we have learned about the different traditional approach of ET computation. Then we have moved to the energy balance modeling. Its overview background we have. Sir, my voice is clear?
Yeah, your voice is clear. Your voice is clear. Yeah, your voice is clear. Go ahead.
Yes, voice is coming clearly.
So, sir, we have one or two query. In that we have just big. So that's what is here, sir. He has in some of UFO translative fraction. Is any criteria to describe the dry pixel and wet pixel? I think that you have shown slides you have presented. But sir,
That has already been
how we can select the dry pixel and the core pixel? Because sir, it is the basis for.
Yes, it has already been clarified. Hello, Vikas.
Abhishek, sir, are you able to hear me?
Yeah, I am able to hear.
Yes, Vikas, are you able to hear me? Hello.
Yes, sir. I am Abhishek, sir.
Yes. My question has already been clarified. I have seen the slides how to categorize dry pixel and wet pixel. So it is okay. Now my another question is, am I audible?
Yes, sir. Yes, sir.
Yes. Sir has told so many browsers to download freely available 𝐁𝐈, 𝐂𝐵, and LST. So 𝐁𝐈 describes the vegetation over the surface. So I wanted to know, is any criteria to describe which vegetation is there, because our areas are having plenty of maize and wheat at the same time. So is any techniques to describe this such area is having wheat and such area is having maize? So this is my one question. Another question is that you have described, you have told how to download freely available 𝐴T and LST emissivity, so many parameters.
Yes, sir.
Is any criteria to validate actual evapotranspiration because after extraction of 𝐴T, it is actual evapotranspiration for our area giving actual or not. So how can we validate this such data?
Okay, sir.
Okay, so there are two clarifications from my side.
Okay, sir. So, very first question, sir, regarding your which kind of crop type is available at the particular area specific. You guys want to know. So,
Yes.
sir, out of total kind of land cover, if I'm talking about how much kind of land cover, like different kind of crops are there in particular season, like let's assume Kharif crop or Rabi crop or in Zaid crop season, particular crop season. So,
Yes.
sir, for that you can use some specific plugins, or you can say a classification algorithm to define the particular kind of crop type within a particular crop season.
Okay.
In terms of product form, there are not such any kind of products for Indian context or Indian Indian cropland specific are available till as my knowledge.
Okay.
But the products are available, but they define only the cropland area.
Okay.
From classified products are available, but they define the only cropland area. Within cropland area, which kind of crops it is available, that you can define based on some ground truth points, some GT points, GPS locations of particular points, particular crop type, and that information you can conclude, or you can add on with some classification algorithms, and you can define how much area comes in the maize crop or rice crop or other kind of sorghum crop, some type, like different kind of crop type.
Okay, sir, thank you. My assumption was that because different crops have different spectral signature. So can you classify according to a spectral signature?
Sir, no, definitely you can define with the spectral signature also. But for the spectral signature also, there is, if I'm talking about Indian context, sir, our farmland size is less as compared to the other countries. Like Now most of the farmers are small and marginal farmers. So our cropland it means particular field to field boundaries are small.
Yes, small, yes.
Small. And in this using the same kind of, like if I want to use a complete classification of Bihar state. So my only the MODIS satellite data cover a single image can cover complete Bihar state. But my MODIS data set has a spatial resolution of pixel size of 250 meter by 250 meter as finest. And when we go for the classification, at least 3 by 3 window has to be confined for particular crop or even the same type of class. So if I'm talking about 3 pixel by 3 pixel, it means almost 750 meter by 750 meter has to be a same kind of crop. Then you can completely define like this is my particular kind of crop type. So this is some kind of limitations when you go for the bigger area. But at the same time, if you want to use for a district level, you can use Landsat data sets. You can use our listed data sets, Indian remote sensing satellite listed data sets, and you can go for the classifications easily.
Okay, thank you. Another clarification is that about AET. After downloading and extracting the AET, how one can validate with the actual situation? Whether it is actual or not.
Yeah, I am coming to the same point, sir. If I'm talking the ET product, these all are ET products are the simulated product, or they are product based on some ground-based observation, some you can say, sir, the satellite-based observations, as well as some radio sound and other kind of observations, the airborne observations, the vertical profile of the atmosphere, all kind of things, such kind of informations. So based on they give you the ET product, because these all are the model product. So they give you the in terms of near to the exact observations, but not exact observations. For that, you have to use some specific ground-based instrument like lysimeter or eddy flux tower or large intercentimeter, perimeter, which are more specific, more accurate as compared to our other kind of data sets. Remote sensing product give you the overall variability in a larger domain in terms of a temporal scale or spatial scale, sir.
Okay, thank you. So one thing is here, can we cross validate the our ET products using those are derived from remote sensing from the I'm getting echo.
Hello.
Can we cross validate the Penman-Monteith
using the ET product, the global ET product?
What we got from the remote sensing, can that be cross validated with the Penman-Monteith?
Actually, nowadays, if you go through a current research trend in the same domain of crop transmission, or in terms of their regional basis crop water use, crop water requirement estimation, people are using, and these are published in peer-reviewed journal when they derive their results using their own parameterized model for their area specific, and they validate some specific ET products, 2 or 3 or 1 or ET products, and they can say like this is my observed data sets, this is my model data sets, and this is the global product data sets. So these are kind of variabilities are there out of all 3. So like the such kind of work is also published in peer-reviewed journal.
Okay.
So such kind of work can be excluded. Can be included when you go for such kind of informations or area specific or region specific, crop specific, total amount of want to know total amount of crop water use or crop transmission.
Okay, sir. So we have 1 or 2 more queries, sir. If time permits, actually, sir, we have exceeded our time. So if you give the permission, I can ask you.
No issue. You can ask me. You can ask me. I am happy to give answer.
Okay, sir. So there was a question from Chiradeep Bhagua.
Yeah.
He was asking, sir, where you have modeled this energy balance approach in ArcGIS or ADAS. So I think, sir,
I did this exercise few steps in ArcGIS and few steps in QGIS, 𝐷𝐶GIS, the part of some other plugins.
Okay, sir. Okay. Means in QGIS
in all kind of plugins are available. If you are easy to handle some new plugins, then you can use QGIS also very easily. Not because in ArcGIS I simply go for some equation based modeling also, and that you can proceed in QGIS also, NV also, ADAS also. Number of GIS softwares are available nowadays.
Sir, he had another question. Two source model is better than one source.
Yeah, obviously.
He has asked.
Yeah, obviously.
Obviously. And do you think wind speed is a major problem in stable model? Because it creates a major problem in iteration to create A and B. Yes, here he is talking about the coefficients after selecting hot and cold principles.
Like wind speed, no doubt, because wind speed and ultimate calculation in terms of aerodynamic resistance. And if you go for if you just go through the detail of the internal calibration of metric model, the important parameter, wind speed is the important parameter, and you have to compute at the near surface like 0.1 meter and 200 meter. At the same 200 meter, the momentum reference length, momentum reference Z1 or Z1 as you calculate. So that important things maintenance internalized calibration.
Okay, sir. So I think these are the two questions he has asked.
Okay.
So now we can close this session, sir. Thank you very much, sir, for your valuable time you have shared with us, sir.
Thank you.
And for rest of the panelists and the attendee, there is a announcement. Tomorrow we will have two sessions. The first session will be on the use of UAV and advanced remote sensing for enhancing water productivity. And the speaker will be Ravi Narayan Sahu, sir. He is the principal scientist at Division of Agriculture Physics, 𝐼CAR-𝐼RI. And the second presentation will be by Master R. Nigam, sir. He is the scientist F at IIRS Dehradun. And he will talk about the hydrological modeling approaches for watershed management specific to the agricultural purpose. So there will be two presentations tomorrow. The presentation will start at 11 a.m. and it will end at the same time at 1 p.m. There will be a separate link for tomorrow's session for both panelists as well as the attendee. So you will get another mail about this session query, and if you have any query regarding this session also, you can write it at the webinar@rpcu.ac.in, and sir will also be available in the panel session which will be held on the last day of this webinar, that is on 9th of October from 12:50 to 1:20. So if you have any query regarding today's presentation, you may ask your questions. We will pass it to the sir on the specific day. So that's all for today, and you will get another link for all the panelists. So thank you very much, sir.
Thank you very much.
Okay, sir. So now,
Okay, thank you. Okay.
Thank you, sir. So thank you, participants.